All right, last problem, number 6 on homework number 2, which is all about energy and energy transfer. Before we really get into the first law analyses of things, so just the basic concepts of energy and work and heat. Number 6 is work is a transfer of energy to or from a system, okay? Now, whether it's to or from depends upon the sign. So if I'm doing work on a system, the sign is positive. If the system is doing work on the surroundings, it's negative, okay? Now, let's say I have 2 moles of argon, okay, in a piston cylinder. So I have a piston cylinder, we've got argon in here, okay. Initially at 1 bar, so P1 equals 1.0 bar, okay, and the volume is, so V1 total is equal to 30 centimeters cubed, okay. How much work is done? So, okay, and I have 2 moles, so N equals 2 moles, okay. How much work is done if I increase the volume to, so V2 total equals 40 centimeters cubed. I want to know how much work is done to do that. But I have 2 processes. I either have isothermal work, so where delta T is equal to 0, and also isobaric, P is equal to 0. Okay. There's some other, okay, so how much work is done if I decrease the volume? So an alternative is V2 total is equal to 20 centimeters cubed, same thing. So work delta T equals 0 equals whatever, and then work delta P equals 0 equals whatever, okay. For the isothermal expansion, compare the work. Okay, we'll get there. So let's do this. The first piece. Okay, so we have our system. We draw in a picture. We draw in what we know. We draw in what we don't know. We're going to put a little boundary around here. Okay, so there's our system. We're going to make some assumptions. Okay, so we're going to assume this is a closed system, that I'm not losing mass. Okay, so closed system. Okay, I'm going to assume I have no shaft work. Okay. Can I assume it's adiabatic? Well, it didn't say anything about insulated, and didn't say anything about adiabatic, so I'm not going to assume that. Alright. I do have boundary work. I mean, that's the whole point of the problem, so I definitely can't assume no boundary work. I need to assume an ideal gas. That's definitely an assumption. Okay. Let's see here. So closed system, ideal gas. Okay, we're also going to assume that the delta Ke and the delta Pe are pretty much 0. Okay, that I don't really, this piston isn't falling from Earth. It's not a rocket ship. It's just on Earth. Okay. There might be other ones that I need to think about, but those are good ones for right now. Okay. So, and then I need to write down my equations. Well, I got PV equals nRT. Okay, that's an important equation. We also have work is equal to minus P dV. Okay. So there's, that seems like all I need to get going on this problem. So now remember, what do I need to do? Draw my picture, draw my boundary, write down my assumptions, write down what I know and I don't know. Now, some of those things don't have to exactly be done in order, but you definitely want to draw your picture before you do anything, because it starts to help visualize, okay, yeah, I got work on this system. I don't have any little hashtags, so it's not adiabatic. Well, there's no inlets or outlets, so it's closed system, and so on and so forth. So let's see here. Okay, so we got minus PdV, so we're really looking at this from a minus PdV perspective of either isothermal or isobaric. Okay, that's what we want to know the work for. Okay, and we did these in class, but let's do it again, so to speak. Okay, so let's do the one that's easiest. Which one's the easiest one? Isothermal or isobaric? Isobaric, because the pressure's constant, so that means I can pull out of the integrals. So W equals minus PdV. Okay, this gets pulled out. Okay, so delta P is equal to 0. So that gets pulled out, and so, and I'm at V1, V1, V2, okay. Okay, and this is V, so I have 30 and 40, okay, so this is equal to minus P dV from V1, V2, which is going to equal P V1 minus V2. Okay. It's okay to skip the math in those steps. I assume, like, I do want to see this one. I do want to see this one and this one, and I want to see you pull it out. I want you to show me that it's coming out of the integral. That's important. Okay. But, from here to here is not as big a deal. Here it's important because it shows me you understand that it's being pulled out of the integral because it's constant, so to speak. Okay. And so I get here, okay, so I'm here. Well, now I can just plug and chug. So 1 bar is 10 to the 5th pascals. Those are 10 to the minus 6. Okay, so I'm really going to have those times 10 to the minus 1. So I'm going to have basically 3 minus 4, or rather, yeah, 3 minus 4, 3 minus 4. Okay, I'm going to do about a joule work, it looks like. Approximately. So, yeah. Because, yeah, I'm going to have 10 to the 5th. And then I'm going to have 30 times 10 to the minus 6th, minus 40 times 10 to the minus 6. Okay, so I got that. So I got 3 minus 4. So I got approximately minus 1. So minus 1 joule. So minus 1 joule. Okay. Actually, I think that's pretty exact. All right, so I got minus 1 joule for doing that work. Okay, but the real question is, does that make even sense? Okay, well, minus work is what? Work into the system or work by the system? Well, I expanded. If I had my hand on that piston, it would move my hand, not my hand move it. So it is doing work on its surroundings. So it should lose energy, so it should be minus. That does make sense. All right, that's good. Okay, so now let's look at it from the other perspective of constant temperature. So we've got delta T equals 0. Okay, now in this case, P is not constant. So I need to know how P is changed by dV based on how the integrals work, okay, based on our numeracy. I don't want to talk about numeracy too much. All right, but I have it right there, okay. So I have minus, let's see here, nRT over volume total dV, okay, from V1 to V2, okay. Well, I know my moles are constant because it's a closed system. I know my R is constant because it's constant, and I know my temperature is constant because it said it was isothermal. Okay, and so when I'm all said and done, I have minus nRT of V1, V2 of dV over V. So I have minus nRT natural log of V2 over V1, which means I have nRT natural log of V1 over V2. Okay, I'm not given a temperature though. Ooh. What do I do? Well, I know the temperature is constant, and I know this, and I know my initial pressure, and I know my initial volume. Okay, so I can plug in here, assuming the same thing. So I'm going to plug it over here. So nRT, natural log of V1 over V2, is going to equal PV1, P1V1, natural log of V1 over V2. And now I can do it. Okay, so again, 1 times 30 was about 3, in terms of joules. Okay, so I've got 3 times the natural log of 0.75. I have no idea. So let's just go put that in our calculator really quick, just out of curiosity, to see how they compare. Okay, so yeah, we have 3 times the natural log of 0.75. So it equals natural log 0.75 equals this times 3. Okay, I get negative 0.86. Now, should I get negative? Yeah, I mean, I still should get negative because I'm still doing work on the surroundings. But I get 0.86. I actually don't do as much work as I do when it's the same pressure. Okay. Why is that? Well, who knows? I mean, it's based on the conditions too. Maybe there's just not a lot of moles, there's not a lot of whatever, maybe it's not hot to begin with. I mean, I didn't actually calculate the temperature. I don't need to calculate the temperature in this case, but I didn't calculate the temperature. Okay. It's just, it's not always that the work isothermal is going to be better than isobaric and vice versa. Okay. It depends upon the initial conditions and the final conditions. How much work is being done. And so, the initial conditions are the same, but the final condition is obviously different. Even though I went to a different volume, because I was at the same temperature, I didn't pull out as much work from the system. My system did not do as much work as it would have done isobarically. Okay, because isobarically, the temperature changed a little bit more. Okay, so the next part of the problem says, so do the same thing but going from 30 to 20. Well, would things really change? They would. You're like, I don't see how. So if I went from 30 to 20, this one wouldn't change, but this one would. Because 30 times 20, 30 minus 20 is still 10. But 30 divided by 20 is a lot different than 30 divided by 40. Okay. So our isothermal work is going to change in this case. And our isothermal work, because we're going from 30 to 20, that's 1.5. Now I'm doing 1.2 joules per work of work. So I'm actually decreasing it by 10 centimeters cubed. Takes the same amount of work if I do it isobarically. But if I do it isothermally, I have to do more work than it had to do to expand it by 10. It's kind of interesting, isn't it? And again, why is that? Well, it's just the way the math works and how the math behaves, and that the fact that this is a natural log relationship. It's just the way the math works. There's really no obvious physical, macroscopic, microscopic thing that's going on. Really, the take-home message from this comparison is there's no best way. Sometimes it's best to do it adiabatic, sometimes it's best to do it isothermal, sometimes it's best to do it isobaric. There is no best way, like automatic. The best way is, okay, you figure out what is the best way and then do it that way. But there's a lot of mathematical different ways to do this differently. Okay. So let's see here. For the isothermal expansion, compare the work done for an ideal gas to that of a van der Waals fluid. You'll need to integrate numerically. Okay. So we did the integration analytically here for isothermal. What do we need to do for a van der Waals fluid? Well, let's kind of erase most of this stuff. I'll see if I can set it up really quick. No, I don't think I have time to set it up because it takes a while to set up my numerical integration. But what you want to do is basically, you have minus PdV. Okay, well then you plug in van der Waals. So you have RT over V minus B minus A over V squared dV. Okay, and I would just use trapezoid formula to go from V1 to V2. Okay, and again, to see how different it is for this system. Now this one I can kind of predict, now not compared to the isobaric, but I can compare the two isothermal cases, okay, because I have that kind of minus relationship, okay. So, you know, that first RT over V minus B, well, that's kind of what I had in the beginning, okay? You know, the V minus B, yeah, it's probably going to be kind of V minus B over V minus B. So even if it's, you know, instead of 3/4, it's, you know, 2/3, okay, that's about going to be the same. But then I get that minus, okay? That minus, that attraction, okay? So I got a minus times a minus, okay? But I'm also integrating a minus. So if I integrate just that part, because I can integrate that part, this is separable. Actually, I mean, technically I can integrate this analytically. It's not actually needed to be, because this one is RT natural log of V minus B, technically, and then this one is plus A over B. So that's actually the integral. So I can do it right now. Why not? So I have RT natural log of V1 minus B over V2 minus B minus A over V2 plus A over V1. Okay. With this minus right here. Okay. And again, we kind of assume that this is approximately the same. I mean, it's not, but it's approximately. It's going to be a little bit. It's going to be a little bit bigger because of this minus. Okay. But really, it's, you know, what's going on with this guy. Okay. But let's ballpark some of this stuff. Okay. Oh, we like to ballpark things, right? Okay. So let's say B has a value. When it's all said and done, let's say B has a value of like 5. Okay, so I have, instead of 3 divided by 4, I'm going to have 25 divided by 35. So it equals 25 divided by 35, okay, equals natural log of that guy. Okay, and if I compare it to my original 0.75, okay, so I'm a little bit more negative there. Okay, so I'm doing a little bit more work than I was before. Or rather, I'm doing a little bit more work than I was before. Okay, but then I have that minus A over V. Okay, so let's say now the A is obviously going to affect the magnitude of things. Now this is argon, so A is probably pretty small. It doesn't have much attraction, okay, or repulsion. So it could have an effect. It may not have an effect. You know, without actually calculating it, but just in general, you know, if I have 1 over 40 minus 1 over 40 plus 1 over 30, well, you know, that's well, equals, so let's just say A is 3. Okay, so A equals 3 divided by 40, yeah, 40. So minus 1/10, because that's what it is, equals this minus 1 by 10. Okay, and then minus that, so 0.025. So so as a whole, that's going to add a little bit, okay, because, well, let's do our kind of our numeracy attached to this. So I have 1 over a big number, or bigger number, 1 over a smaller number, okay, minus, plus, so 1 over big is small, 1 over small is big, okay, and so I'm going to add basically a little bit to this, adding, obviously, the sign of adding is I'm doing work on the system, but really I'm just counteracting work done by the system. So this was a little bit more negative, but this is a little bit more positive. So in this case, especially because argon is an ideal gas, it might not have any impact. But really what you have, the thing to kind of take home is that the exclusion volume, okay, this B, is going to make it so that I'm doing more work, okay, in this expansion. It's easier for me to do more work because there's less volume I need to produce, because I've got all that volume excluded by my own self. Whereas an ideal gas has to produce all of the volume. Okay. But here, it's going to decrease it because, well, really, if you think about what's kind of expanding it, it's in a sense pressure. You've got things bouncing around and it's moving the boundary. Well, the attractions, what do the attractions do? They make it so they don't bounce out around as much. And so they're not as attracted to the wall, they're attracted to each other, so they're not bouncing as much against the wall. So this is going to take away from the compression, the expansion work. So this is going to take away from the expansion work, and this is going to add to the expansion work. Whether or not they counteract each other really depends upon the gas. And that's kind of the take-home message I wanted you to get from this. So what are all the take-home messages? Okay. Isothermal versus isobaric. One might be bigger, one might be smaller. It depends upon the conditions. We found that in isothermal expansion, it produced less work than an isobaric expansion, but an isothermal compression required more work than an isobaric compression, okay, for an ideal gas. The other thing we learned was that the attraction term in van der Waals is going to make it so that it will not produce as much expansion work, okay, because it's not expanding against the boundaries. But the volume exclusion is going to help because it's less volume that it has to produce. But again, they might cancel each other out, so to speak. So that's the homework for this week. Stay tuned for next week for homework 3, departure functions, or as the rest of the world calls them, residual properties.